All right, the final talk in our session is going to be delivered by Wang, who's at the National University of Singapore. And he's going to talk to us about program skeletons for automated program translation. Thank you, Bo.
Okay, so hi everyone, I'm Bo from National University of Singapore. Now I'm going to present our work on code translation. So the title is Program Skeletons for Automated Program Translation. This is a joint work with Tianyu, Ruishi, Umang, and Prateek. Okay, so first, why do we want to translate programs across different languages? There are several possible motivations. And first, when we want to migrate legacy code to modern languages. So this figure shows that the popularity of programming languages, they're changing in the last 20 years. And sometimes we migrate the code base because the distribution of software is shifting. And the second, from the software security perspective, we want to move code written in memory unsafe languages to safer alternatives. And third, sometimes there exist some useful libraries written in one language, such as Python, but developers in another language, such as JavaScript, they want to have some similar functionalities. And automated code translation can help there as well. Okay, so despite its potential usefulness, we don't really have much success in this problem. There are at least two requirements for the task. So first is correctness. So means that we want the translated program to have external, the equivalent external input-output behaviors. And the second is scalability, which means that we want the translation mechanism to be able to deal with realistic long software. And so people have been working on this for a while. And 25 years ago, there was an interesting technical report on the experiences of real-world code migration. At that time, a comment that language conversions are as easy as turning sausage into a pig. Basically says that automated language conversion is much more difficult than many people anticipate. Okay, so why is it difficult? So let's look at a very small example with 2 lines of Python. It creates a dictionary object and prints a result. So assuming we want to translate this piece of code to JavaScript. So traditionally, the traditional way of it is building a compiler. So we indeed have some Python to JavaScript compiler. If we give it to the compiler, it will give us some code like this. So we can see that first, it looks more verbose than the source. And second, if you look closer at the code, we'll realize that the translation is actually emulating a lot of stuff in Python. So including data types, APIs, and all these emulated constructs are injected by the compiler. So essentially, the translation is trying to lower the Python code to a subset of JavaScript with emulated language constructs. So such translation is far from ideal when we want to migrate software. And this phenomenon is not specific to Python and JavaScript. So I'd like to quote the same report that basically investigate COBOL and to Java translation. But here we said, you could call such translation JavaScript compliant Python program, but not necessarily JavaScript programs. Okay, so more specifically, such translation has 2 main issues. First, it is very hard to preserve every detail of the source. So you end up with ugly code when trying to be correct. And the second, it may defeat the purpose of the translation. If you want to migrate from legacy dependencies, it preserves all the legacy dependencies. If you want more performant code, and you might be disappointing if the translated code is a lot of emulation. So let's revisit the requirements of automated program translation. The correctness and scalability are probably the most explicit requirements, but there are also implicit requirements, such as we want the code to be readable, maintainable, using native language constructs, etc. Or in one word, we want the code to be idiomatic. So this shouldn't be overlooked since, as earlier work also mentioned, imaginary advantages often motivate the conversion process. So as we all know, 20 years later, we have code LLMs. And if we give such a piece of code to these models, it will produce translations that are much more idiomatic. However, as basically evaluated in various previous work, these models work fine for small pieces of code, but struggle to produce correct translation when dealing with slightly longer programs. So in this paper, our main contribution includes the following. First, we propose a technique named program skeletons that allows idiomatic translation of long programs. And second, to basically go with the skeleton, we propose a common abstraction of program semantics that is suitable for the purpose of translating across language. And third, we implement a prototype named SKEL, which can handle realistic Python programs up to 2,000 lines of code. Mostly automatically, yeah. So let's first look at the high-level idea of program skeleton. So it is actually quite simple. Given a source program, we decompose it into a skeleton and associated code fragments. The skeleton is basically an incomplete program with holes. So then the skeleton and the fragment will be converted to the target language and get composed into a complete translation. So to demonstrate how it actually works, let's first start looking at an example Python program. So assuming this is a Python program we want to translate, we don't need to understand the statement level details, but only look at a high-level structure of it. So the entry point of the program is a code in the global scope, and here the entry point has some whole program tests. And besides the global scope, we have two top-level functions named compute and multi. So within the function compute, there's a nesting closure definition with function name update. So note that these code fragments will actually interact with each other if we execute the program. So if we roughly look at the execution behavior, the execution will start from the entry point, which is a whole program test, which calls the function compute. And within function compute, it will try to call another function multi and passing the closure update. And then within the function multi, it will try to loop over an array and call the closure. So overall, this function has three functions, including one escaping closures and 4 lexical scopes in total. OK, so if we want to translate this using program skeleton, we will first offer using a syntactic decomposition of it. So basically decompose it into a skeleton K and code fragments G0 to G3. The executable code inside each lexical scope is one fragment. So now we have 5 pieces. We can start to construct the translation. So we can perform a direct rule-based conversion of the skeleton, which will deterministically produce a mirroring skeleton in the target language. And then for each code fragment, we can use LLMs to produce candidate translations and then try to fill in the holes of the skeleton. So since we cannot really trust the LLMs in the generated code, we need to somehow check if those code fragments are correct. So this can be tricky to tell whether the translated fragment is correct because idiomatic translations, first, they look very different from the source. And then second, these fragments may interact with other code fragments in various ways. So the question is, what kind of program behaviors should be considered equivalent in our translation task? So there are several ways to think about the problem. We need to find a common way to model the semantics of the source and the target. So first, we may consider modeling each piece as a pure function. So including the skeleton itself as well as the fragments, so if we model each of them as a pure function, and also if we can somehow replicate the same set of pure functions in the target language, and if we can check their input-output behaviors, and if they match up, we say each fragment is equivalent and the whole translation is equivalent. So such a style of semantic modeling is probably suitable if the code is pure, but not a suitable choice if we are dealing with procedural code with different kinds of side effects. So to naturally capture side effects, an alternative way to model the problem, to model the semantics, is to consider the program as a state transition system. So in such a model, control flow transfers between code fragments, and this transfer will be associated with state transitions to a shared memory state, so represented by a RAM module in the figure. So however, the problem of such a modeling is that such memory states, they will capture low-level details that are language-specific and may not actually transfer over to a different language. So for example, consider the for loop in the program we showed earlier. If we look closer at the memory state, at the time of control flow transfer to a different function, we will see that there are stateful objects and variables such as iterator zip or variable x that doesn't necessarily make sense for the other language. So what kind of semantic abstraction is suitable for a translation task? Ideally, we want our common semantic model to achieve 3 goals. First, capture side effects. And second, abstract away low-level language-specific details. And third, it should allow some decomposition, which means that if we can determine the equivalence of individual fragments, then we should know for sure that when we combine, the combined translation is definitely correct. So we can see that pure function not really suitable and or straightforward for modeling code fragments with side effects and shear state transitions. They capture too much low-level details. So what is a better way to model the problem? So we propose to model the execution of code fragments within the skeleton as a set of communicating processes. So conceptually, we can think the program skeleton K as the process 0 that communicate with fragment processes, for example, P1 and P2 in the figure. So each process has private memory states that is external to the process. So the only way for processes to exchange information is by communicating through messages sent and received between the processes. So in this abstract model, we expect a correct translation to replicate similar semantics, basically the same set of process and the same messages in and out of these processes. And we consider it is sufficient for the translated fragment to be considered correct as long as the messages are equivalent to the source. Note that it does not require the internal states of these processes to be equivalent across the languages. Okay, so far we have explained the high-level idea of program skeleton. To build a runnable prototype to test it out, we implemented a tool named SKEL that translates Python to JavaScript. So we made several design choices for practicality considerations. First, we focus on dynamic analysis and correctness under test. So the benefit is that the analysis of APIs, loops, recursions, and dynamic types are made much easier. The downside is that it can be incorrect if the tests are insufficient. We use a rule-based compilation of the skeleton, and the benefit is that ideally it can work regardless of the program size. The downside is that we do assuming that the translation has a common high-level structure with the source. And we use the LLMs for synthesis of code fragments, and it gives us readable and idiomatic code. The downside is that there's no guarantee that LLM will give us the correct result every time. So when it fails, the mechanism needs to somehow deal with it. Okay, so more specifically, SKEL works in 2 stages. The first stage focuses on skeleton generation. So SKEL takes an input program, normalize it, and then generate a synthetic skeleton. So with the generated skeleton and the decomposed fragments, we perform dynamic analysis to collect traces that are basically expected messages in and out of the processes in our semantic model. So these pieces of information basically give us the syntactic and semantic constraints of our translation task. And the second stage is to reconstruct a program in the target language satisfying those constraints. So we have 2 goals in the second stage, basically the translation stage. So first, we want the constructed target program to pass the test by construction in the ideal case. And secondly, if error inevitably happen in the translated program, they should be isolated to an individual process. Like we should be able to know precisely which code fragment is the root cause of error. And otherwise, if the error propagates, we will not be able to know where to fix. So our solution for the second stage, the translation stage, is a procedure named execution order translation loop. So it works by performing the translation incrementally, following the natural execution order of the program. So in the beginning, we only have the target skeleton without any field fragments. So as we execute it on the whole program test, the translation procedure will gradually fill in the translated fragments and check step by step. So at each step, we only check for the corresponding to one random interaction with a single process of some code fragment. So for example, if the check pass, then we simply it means that fragment at that execution step produces expected outcome, and we continue with the next execution step. Okay, but sometimes the check didn't pass, and which means that an error might exist in the corresponding code fragment. And in that case, the translation procedure will refine the translation query as well as performing iterative repair until it passes a step. So ideally, with a powerful enough LLM, after such translation loop terminates, we are guaranteed to have a whole translation that passes the test. In reality, is that when LLMs cannot resolve an error after retry a limit of 3 times, the procedure will pause until human users fix the highlighted code fragment so that the procedure can continue. So to evaluate scale, we collect a benchmark of 9 Python programs with length up to around 2,000 lines of code. 3 of them are modules from the Python standard library, 2 of them from popular repository on algorithm implementation, and another 4 popular Python libraries from GitHub, each with around 700 to 1,000 lines of 1,000 stars. So this figure shows a result. We run in scale with both GPT-4 and GPT-3.5. The green bar shows the percentage of code fragments that are automatically handled by scale. And the orange bar shows the fragment of code fragments that needs to be fixed by human to allow the translation loop to continue. So overall, scale with GPT-4 can automatically handle 95% of all the code fragments, and scale with GPT-3.5 can handle 85%. So it is worth noting that after the translation loop terminates, all output program pass whole program tests. So we also show how scale compare with baselines in terms of how much user fix is needed. So here we choose our first baseline as a GPT-4 with a simple strategy that basically translate function by function. And we choose our second baseline as transcript, which is a compiler-based tool that translates Python to JavaScript. If we sum up the numbers of user fix, scale with GPT-4 requires 23 fixes, or 5% of all the fragments. And GPT 3.5 requires more fixes, but is still lesser than the baseline with GPT-4. So besides the numbers, it's also worth noting that it is more difficult to debug and fix the baseline translation, since we don't know where exactly the bug is. Because sometimes if we just run the program, the report runtime error, it may not necessarily be the bug. But Scale does not have the problem because it has the semantic checks, and it will report to the exact fragment needs to be fixed. We can also see that the compiler-based transcript is not able to run on 5 of the 9 programs. It is because that these programs use language features and APIs not supported by the compiler. Okay, so to summarize, program skeletons offer a promising decomposition of the code translation problem. And there are definitely more work need to be done to eventually turn sausages into pigs. For example, we need to handle more APIs, different kinds of external effects, file network, and etc. We also need to support more language features, such as multi-inheritance. And it's also interesting how this can be extended to other pairs of languages. Yeah, that's all. Thanks for listening.
Thank you.
Hi, thank you for the talk. I'm Jose, University of Edinburgh. I want to ask you, if I want to use your technique in arbitrary languages A and B, what should A and B be like? Like how similar or how different they can be so your technique would work on them?
Oh, right. Yeah, okay. So the question is about if we want to use it in other languages, how similar should the language? Yeah. So this technique is probably works the best for untyped languages. It is designed for untyped languages, but it can be also extended to other languages. I mean, static type languages, or like if it's procedural code. But for static type languages, I mean, we probably need more work. So what the semantic analysis in this paper is not sufficient, for example, to deal with C2 Rust. Yeah. So that will probably require more advancement. Yeah.
Hi, Michael Ficara, F5. My question is about performance, not performance of the translation process, but performance of the output program. It wasn't mentioned explicitly as success criteria that the programs would have similar performance, but I'm assuming that it should be, and assuming that it is it possible that that goal would conflict with the desire to create idiomatic programs? I'm thinking as an example, 2 different string types in different languages would have different performance characteristics because one might store it as like UTF-8 encoded, one might store it as like a sequence of code points, and then the same string operation would have different performance. So is that possibly in conflict with the making it idiomatic?
Yeah, okay. So what we didn't mention in this talk is that it actually has a type mapping. So for this semantic check to work, there need to be a mapping of objects and types. And for that, I think it can be customized. It can be changed if you prefer a specific data type. And in that case, the translation is forced to use that type. So it should be like be customized for your job. Yeah.
Yeah. Thanks for the great talk. It's a really interesting project. And I was wondering that is there a clear boundary or a clear guideline to make the skeleton to implement the skeleton technique? So the syntactic structure of the source language and the target language could be different. For example, if you want to translate a for loop, there could be many ways to implement the for loop in the target language. So, but if I force the target language to use a specific loop structure, it's going to lose some idiomatic structure in some ways.
Yeah. So actually, we try to present. I guess it's kind of one general way to decompose the program. And so the way we are dealing with it is that we simply decompose by the lexical scope, and all the executable code within lexical scope is one fragment. But the same idea can be applied, for example, if you want a for loop to stay similar, you just decompose the inner part of the for loop. And you can still model them as fragment processes. Just there are slightly more analysis need to be done to figure out what is the input and output of those processes. Yeah.
Right. We have time for just one last question.
Hi, Leonard from University of Montreal. So thanks for the talk. I had a question around semantics. So sometimes semantics around languages, even a simple for loop can be like completely different. And I know here your goal is to like keep it idiomatic, but I was wondering if you could share maybe some insights around how you can deal with these cases where, for example, in Python you cannot put anything in a body of a lambda. Yeah.
Yeah. Okay. Yeah. So I think the mechanism is designed specifically for that. So you can do arbitrary things in Python. You can put a for loop in a list comprehension, but the analysis only observes the communicating messages of that conceptual process or what will be in and out of the fragment. So it will observe, for example, several function calls out of it, and it really doesn't care how you initiate these function calls. So you might initiate using a comprehension or a for loop or just a bunch of repeating statements. So it will be considered equivalent.
Great. And with that, we close out a great session. Thank you, Bo. And let's thank all of our speakers.